Now, let's think about how I can apply this idea of elimination to find the inverse matrix, which solves the more general problem no matter what vector I write down on the right-hand side. So I have a 3 by 3 matrix A and its inverse B, which are multiplied together to give the identity matrix I. So before we had the matrix for A was 1, 1, 3, 1, 2, 4, and 1, 1, 2. And B here is I'm going to actually introduce some notation. I'm going to call B composed of elements B11, B12, B13, where the first digit represents the row. So then I'll have B21. The second digit represents the column. So this would then be B22, and this one would be B row 2, column 3. I'll have B31, B32, B33. So that's the row, and that's the column. Equals I. And what we're saying here is that B is actually the inverse of A. So that is, if I multiply A by its inverse, I'll get the identity. And actually the inverse is special because I can do it either way around. I can apply it to A on the right or on the left and it'll still work. Because I times the inverse of A is just the inverse of A, so it doesn't really matter which way round I do it. But I'm just doing it here so that I've got some B's to play with and I don't get confused between my A's and my B's. Right? But for this example, I'm saying B is the inverse matrix of A. Now, notice that this first column of B here is just a vector. It's a vector that describes what the B matrix, the inverse of A, does to space. Actually, it's the transformation that that vector does to the the x-axis, if you like. So, and the identity matrix is just 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So I could write this down. I could write down this A, that big square guy, times B11, B21, B31, and I would get just the first column of the identity matrix, 1, 0, 0. Now, I could solve that by my elimination method and back substitution, just in the way I did before, except I'd be juggling different numbers here. Then I could do it again for the second column of B, the second vector of B, for the second vector of the identity matrix. And I could do it again for the third one. So I'd be doing that in some series, if you like. But, here's the fun bit, I could do it all at once. So I'm going to do this process of elimination and back substitution all at once. I'm going to do it for all the columns on the right-hand side simultaneously. So if I take the first row here and I take it off the second row, as before, I'm going to get rid of this one. And if I take the first row off of the third row, I'm going to get rid of both this one and this one. So if I've got, put the unaltered ones down here, 1, 1, 3. If I take that off of the second row, I'm going to get 0, 1, 1. And if I take that off the third row, I'm going to get 0, 0, minus 1. So on the right-hand side, I'm going to have the unaltered one is 1, 0, 0. And I've taken that off of the second row. So I've got taken 1 off that. That's minus 1, 1, 0. And I've taken that off of the third row as well. So I've got minus 1, 0, 1. And so now I can multiply that third row through by minus 1. And that's in the form I then want. Well, I've got 1's on the leading diagonal and 0's below it. So when I multiply that through by minus 1, I get a plus there and a minus there. Now I can substitute that third row back into the second and first rows. So I can take one of it off of the second row and I can take 3 of it off of the first row. So now the unaltered one is the bottom one, 1, 0, minus 1. If I take one of those off of the second row, then I've got 0, 1, 0 there. I'm going to take that off of the second row over here. So if I take 1 off of minus 1, I get minus 2. Take 0 off 1, I've got 1. take minus 1 off of 0, I'm effectively adding 1. Then I want to do that again to the first row. I want to take 3 of them off to make this guy here 0. So I've got then 1, 1, 0 there. And I want to take 3 of these off of the first row. So I take 3 off of 1, gives me minus 2. Take 0 off there. And I've got to take 3 of minus 1 off of 0, so that gives me plus 3. So we're nearly there. I've just got this irritating one here. I've got to take this row off of this row, and I'll be home. So if I take my third row is unaltered. Let's put some brackets in. My third row is unaltered. My second row is going to be unaltered. 1, 0, minus 1, minus 2, 1, 1. If I take that row off of that row, then that altered one gives me 1, 0, 0. Take the 1 off there. Take this row off of this row, minus 2 off of minus 2. I've got to take minus 2 off of minus 2, so that gives me 0. Got to take 1 off of 0, that gives me minus 1. And I've got to take 1 off of 3, which gives me 2. So that's my answer. So now I've got the identity matrix here for A, in effect. I've transformed A till it's the identity matrix. I've got my B matrix, which I haven't really changed. And my identity matrix over here I've changed. So now I've got an identity times a B matrix is equal to this guy. So the identity times something is just itself. So this is, in fact, my answer for the inverse of A, or B. So I've found a way here to find the inverse of a matrix just by doing my row elimination and then my back substitution, which is really cool. So what we've done is we've found an inverse matrix, A to the minus 1 here, and if we multiply A times A to the minus 1, we'll get the identity. And prove to yourself, if you like, just pause for a moment and have a go at doing that for yourself and verify that that times that does in fact give you the identity matrix. And in school you probably did this a different way, but computationally this way is much easier, particularly when you come to higher dimensions, 100 rows and columns or something like that. There are computationally faster method of doing what's called a decomposition process. And in practice, what you do in any program that you write is you simply call the solver for your problem, or the function, something like inv A, or whatever it is, and it will pick the best method by inspecting the matrix you give it and return the answer. But the point here is to show how these problems are actually solved in a computer, and also we'll observe some of the properties of these methods in different circumstances that will affect the sorts of things we want to do when solving these sorts of problems. So what we've done here is figured out how to solve both sets of linear equations in the general case by a procedure we can implement in a computer really easily. And we've made that general by finding a general method to find the inverse of a matrix in the general case for whatever is on the right-hand side of our system of equations. And hopefully that's really satisfying and really nice.